now you should be able to hear me. Hi together. My name is Nick. Unfortunately, I'm alone today, doing this presentation on my own as François is ill. But nevertheless, great to be here. Just maybe 1 second about me. I work as consultant for a small consulting company from southern Germany, Digital Frontiers, and with this being said, just let's dive into our talk. 502 Bad Gateway, why zero downtime is more than just a config. And before we really start into our presentation, maybe take a second and think back, when did you last use a USB drive to transfer files from one computer to another? And probably, okay, can't click through my presentation like this. Maybe now it's working. And I'm pretty sure we all know it's been a while. So why has it been a while? The files are stored somewhere in the cloud. I mean, this presentation, it's stored on some Google servers, and it's available on my smartphone, on my tablet, on my computer, on my private laptop, on my work MacBook. It's just there. I don't have to care for it. And this is how our users are used to use applications nowadays. Somewhere stored in the cloud, it's always available. It's someone else's problem. But it doesn't stop right there. It's the same for us developers. As developers, we think like, yeah, well, we have to store it, or we have to run our application. Well, just run it in the cloud, then it's always available, it's always there. Someone cares that there are enough resources. Someone cares that our applications are restarted when they are failing. And so it goes on. I mean, the team who runs actually a Kubernetes cluster, for example, they have the same, or they can have the same mindset. The servers that are needed to run our clusters or our worker nodes, they come from somewhere. There's someone managing them, and we can just deploy our Kubernetes there and run it. And when we have to patch something, well, then we take down one node. There are enough resources to just scale up another node. And well, we can do this for quite a while, but at some point, someone has a problem when something fails because they don't have a failover. When you think about an infrastructure team, when a server is crashing, then it's crashing. There is nothing they can do about it. So, and when some server is crashing, well, then in the worst case, it ends up somewhere in the news with some, bad things like, I don't know, 50% of the internet isn't working anymore because Google lost an availability zone, or AWS lost an availability zone. And of course, these are really extreme cases of unavailabilities, of 502 errors. But in fact, it's more than just the loss of a whole availability zone that can get us there, because the someone else's problem is really only valid for one user group, not for the technical users like we are, but for typical end users. Well, yeah, they don't know about things like cloud or how they can do better. They just have to rely on the software. But all other groups on this slide or in this picture, they should have known better, and they should have cared about things, or they should have cared how things are handled if something crashes in the cloud. So obviously, the promise that the cloud makes everything better is not really working out, or someone else is caring for everything isn't working out. So maybe then the answer is back to the roots. Just skip this whole cloud stuff and do some traditional setup. We have our feature teams that focus on delivering new features, that focus on delivering new values. We have a delivery team strictly separated, caring about things like, how are those applications, or how is this code actually bundled? How is this code deployed to production or to other stages? How is it tested? How do test managers approve the code that goes to production? And of course, we have also strictly separated our operations teams running the database servers, running our application servers, and caring for all this hardware. And maybe this is the answer? Well, I mean, we didn't do the cloud thing just for the availability, right? We do it for lots of other reasons. I mean, have a look at it. We develop more and more features nowadays. IT is more and more a core of each and every business. So there are more applications that are entering the stage. Our applications consist of more and more deployment units in terms of microservices and microservice architectures. So when all those new features or all those new applications are crashing on a team that actually doesn't have a primary job of running applications, but of running the servers, then it gets really, really crowded. And of course, it's also quite chaotic. I mean, we had times when we did deployments 2 times a year and everything was working. And in between, well, we delivered features, or we developed features, but we couldn't deliver them. But unfortunately, features only deliver value when they're actually live and in production. So we cannot wait until those features are dusty and can be deployed to production, but we have to deploy them to production quite often and really fast. So this just increases the bottleneck with those operations and delivery teams. And furthermore, when we deploy more often, we can't allow us a downtime each and every time. So it really needs knowledge what has to be done to get this deployment right. So this is another point that's clearly for an end-to-end responsibility. And this is only possible when our teams or we developers are enabled to actually deploy to production. The next point is when we think of a traditional setup, we have maybe a WebSphere and Oracle, and that's it. This is our tech stack. This might be suited for times when we developed, I don't know, 5 applications, maybe 6. But nowadays, when IT is core of our business value or delivers core business value, this often isn't enough. And the cloud gives, and cloud offerings really help us and to get a great variety of products that we can choose from. There are traditional SQL databases, NoSQL databases, object stores, different messaging systems, and so on and so on. And this just can't be managed without some external offering. And the most important thing, after all, we need a clear end-to-end responsibility for a whole product, for a whole service, for the whole application. No blaming some ops blaming the devs blaming the ops, everyone hating the delivery team because they are just doing the wrong things at the wrong time and nothing's working out. So the cloud is great because it enables us to deliver software to production quite easily, quite often. It enables us, or it provides us with a variety of different technologies we can choose from, and it enables us for an end-to-end responsibility. So DevOps it is, and hopefully not DevOps like on this picture. Just skip out this whole delivery and operations and call it cloud and rebrand your developers to DevOps engineers and everything's fine. That's not how cloud or how DevOps should be working. So how should it be working? First of all, we need to be aware that the teams that did operations earlier are still needed. I mean, someone has to manage the infrastructure. Not when it's bought, okay, when you rely on some complete setup from Amazon or Google or Microsoft, but when you have an in-house cloud or an in-house cloud offering, you still need them. But you even need them more in the DevOps teams. I mean, those guys run services for years, and they didn't even know what they were running. Now, when we pull them into the feature teams as DevOps engineers, they know what software they are running. They can directly talk to the developers and know what it's all about, what they have to operate. And that makes it much more easier. But of course, the practices that they have, like monitoring, log file analysis, correlation of application and system logs, and whatever they did, you still need to do it. It's just not some central team that takes care for log file analysis or things like that. But it's each and every developer. It's a mindset change that the DevOps teams have to actually take care and responsibility for their services. They are the ones who are responsible that everything is running. So the monitoring is a big part of it. And who is better suited to set something up like that than the guys who did this for years? And with this being said, let's get a little bit more technical on how we can actually do zero downtime deployments. The first thing, it's quite obvious, for zero downtime, we need more than one instance. So it's just not about running one instance of our servers, and when it's not available because server's failing or something's failing, well, it gets restarted, but still there isn't downtime. More important, for deployment of a new version, you just can't take down one service and no one answers. So you need more than one instance. Speaking of Kubernetes, it's done quite easily. You define some replicas, in this example 4. So there are four instances running of the service, and we define how updates to new versions should be done. They should be done rolling. There's some more context that are typically set, like max search, telling Kubernetes how many So max search of 25% tells Kubernetes that there might be more than this 4 replicas available. 25% more than this 4 replicas might be available. That's the max search. And the max unavailable. The max unavailable tells Kubernetes that at least, or at most, 25% of our desired 4 replicas may be unavailable during an update. This being said, it's a config, it's quite easy, and Kubernetes does its job. But Kubernetes isn't the only one involved in such an upgrade. There are implications on the application. And to just picture, there's just some small picture to show these challenges. I mean, we have our container or our application running in a version 1 and a version 2, and they are running in parallel during an update or during an upgrade. And this means when traffic is entering our system, it's directed to any of those 4 instances. So it might be targeting a container of the new version, it might be targeting a container of the old version. The question is, how can we handle this when there are things like API changes? It is something our front ends have to take care of, or our callers have to take care of, have to be aware of. So there might be orders of the deployment of front end and back end and so on, and all those things you just can't deliver them or can't move this responsibility to some external team. It has to be the feature team that actually knows those dependencies and that has to take care of during the development of those backend, front-end services, that the front-end is able to talk to 2 versions at the same time, or that the backend redirects smart to the new version or something like that. It is something we have to take care of. And it's not only the traffic entering our system, it's also the persistence of our application that has to be taken care of. I mean, there might be schema changes in our database or in our storage system. So at the same time, schema in the old version is written, or data changes in the old schema are written, and data changes in the new version might be written to the database. Or even both versions need to be served at the same time. So it's really challenging to do it. It's not just one config, one property, rolling update, replicas 4, and we're done. To get really rolling deployments, our applications have to be able to handle this. There are answers with tools like Flyway. You can, for example, first spin up the new schema and transfer the data while the whole application is still reading and writing, or reading from the old one and writing both ones. There are possibilities, or there are options to do it, but we have to, for each and every feature upgrade or for each and every update, we have to answer these questions. We have to ask ourselves, how do we really make it zero downtime so that our end users won't experience any failures? And of course, it's not limited to the database. You have the same issue with incoming messages, for example, from a messaging system like Kafka or anything. Each and every upgrade in the cloud that is done with zero downtime has its challenges, and we have to be aware of them. The next thing that is really important to get an upgrade or to get a deployment might not only be triggered by updates or by feature or by upgrading to a new version of our service, but might also get triggered because some workers are shut down or something like that. The application has to know, when am I ready? When can I actually serve traffic? In Kubernetes words, we can easily configure this by configuring a startup probe. Please don't do things like we use liveness probes and availability liveness probes and readiness probes and work with some initial timeouts like that. No, use the startup probes. They are exactly for this. They're there for this reason, that a service might take its time to get up and running. And exactly this is what the startup probe is all about. It is started when the container is created. It's running until it gets checked until the container is up for the first time. Then the readiness and the liveness probe can take over. So choose it wisely. The next thing I already talked about, the liveness probe. You should configure something meaningful. And with something meaningful, I mean not what is depicted here, just use the actual actuator health endpoint. We'll get to this later, but something meaningful, think about what you configure here, what actually can tell Kubernetes if your application is running. The next thing to do is the readiness probe. With this probe, you can configure, or you can tell Kubernetes if your application is ready to handle traffic. So only when the readiness probe is fulfilled, the ingress will direct users or traffic to your application. It looks quite similar to the startup and the liveness probe, with just one difference. It tells readiness probe. It's called readiness probe. So the point is, I already said it, don't just rely on those default probes. Why? Well, first of all, maybe your application can serve traffic when it's not connected to your Kafka bus. It might not be fully functional, but it can still serve user traffic for reading access or for read access, for example. Or you have some event sourcing architecture where you actually are able to replay all those events when the Kafka is back up. So why on earth should you just or why on earth should Kubernetes restart your pod or stop serving traffic to your pod just because Kafka isn't available? It might get even worse. You implement custom health checks. They are a useful tool to get an overall insight into your application. For example, when you have to monitor if your application is doing well, is being able to fulfill all its features, you have to know if third-party services are available. But those third-party services might be unavailable, and your application should be able to handle this. But when you just rely on those default health checks, and you have custom health checks that you get this insight, that you get this monitoring insight, you shouldn't shut down your application or stop serving to end users just because some health check is down. So while it's a really useful tool to have custom health checks to get a good insight, here on this slide, we have just some very, very simple custom health check with Spring Boot. It's really a no-brainer to implement them, or the technical part is a no-brainer. Of course, you have to think about the logic that actually tells you when your application is not available. But the technical part is easygoing. You still have to think which health checks should be included in readiness, in liveness, and in availability, and in readiness probes. And to do so, Spring Boot helps us with two custom endpoints. One is liveness probe or /health/liveness, the Spring Boot actuator, and the other one is the readiness endpoint. Both of them have some basic default from Spring Boot. The first one, the liveness probe, just tells, okay, in principle, this application can run. So all dependencies expressed through beans and so on, all dependencies expressed through properties can be resolved. The application can be started. That's what Spring Boot does for the liveness probe. And for the readiness probe, it actually waits until the server is started, the database connection is available, and potentially Kafka connections and stuff are available. But still, think of it, what do you really need? And with this being said, you can reconfigure them. You can just, by adding some properties, you can define which probes should be, or which health checks should be enabled for which probe. Here, for example, we reconfigure the readiness to not only include the readiness, so that everything was connected once, but to also monitor the database. For example, if you mostly rely on writes to the database, when your database isn't available or your pod cannot reach your database, you shouldn't serve traffic. It's better to show a generic 502 page that tells the user that something is wrong, instead of directing them into your application and failing with some internal server errors. And of course, you can also programmatically change those states quite easily with Spring Boot code on this here. So after having talked about the whole startup thing, that Kubernetes knows when Kubernetes or when a pod is ready to serve traffic, it's also about stopping those applications. I mean, stopping an application is quite easy, sick kill, and hopefully everything is working. Well, that's not how it should be, and it typically isn't how things were shut down in the good old days with on-premise setup. And of course, this isn't a thing we should do in the cloud. So what could go wrong? Why is it so important to have a controlled shutdown? When we look at this picture, the user does a request, and while our service is processing this request, before it can actually answer, the control plane zone Kubernetes tells the service sick kill or sick turn in the first place, and the request is aborted. It might get even worse if you have some background jobs running that might run for, I don't know, 30 seconds, 60 seconds, 90 seconds. They are just aborted in a completely undefined state. To prevent this, first of all, what could our application do? Well, the first thing that's really easy going with Spring Boot, we can configure our shutdown to be graceful. What does this mean? Actually, it means that on a SIG turn that the cluster sends to our service when a pod needs to be shut down, Spring doesn't just stop the Tomcat, but instead it waits until open requests are finished. The same for example, Spring Cloud Stream Kafka integration or something like that. They also wait until the currently processed or the currently handled messages are completely processed, or at least they wait until a certain timeout is reached. That can all, of course, also be configured. And when we need some custom logic, I just talked about having some background workers or background threads that are running for some seconds to do some background jobs. Maybe we have to stop them or put them into a defined state so that they aren't just interrupted. Of course, we must be able, or we should be able, to handle hard interruption, hardware failures happen. But for the average case, for the good case, that is done most often, we could write some custom logic that handles this. And how can we do this with Spring Boot? Well, there are so-called smart lifecycle beans. And those lifecycle beans allow us to run custom logic upon creation or upon startup of the application and upon shutdown. And like with the Tomcat that is still finishing requests, when we have configured a graceful shutdown, then we get the timeout phase, or at least at maximum, the time configured for each and every phase to run some shutdown logic. And afterwards, after our timeout is over, then we are killed. So this allows us to finish or to write some state back into a database or something like that. And of course, there's also the Kubernetes part to it. First of all, we can configure some scripts that are executed on SIG term. So before the application is actually shut down, we get a SIG term, and we can handle, actually before we get the SIG term, something might be executed. In this example, it's just a simple timeout. Maybe our ingress needs some time to actually process this shutdown or whatever. And of course, when we actually do some cleanup, we have to configure some period that the Kubernetes cluster waits before it actually switches from SIG term to SIG kill. So, and now before going into the next things we have to take care about, let's just have a look at, or a simplified look at a Kubernetes cluster. Typically, our cluster consists of more than one worker. In this example, we have 3 workers in our cluster, and we are running 3 applications. We run applications A, B, and C. And when we now have a look at this picture, we can all tell what's happening when node 1 has a hardware failure and is shut down. Or what happens when node 1 is taken out of the cluster because it needs to be patched or updated. So the Kubernetes needs to be updated. Then application A is not available anymore. Application B still has 1 container left, so it can serve traffic. Application C is unaffected, but application A is unavailable. this is not how things should be. And to prevent such scenarios, like with this application A, from happening, we can configure our deployment that it won't happen. So yeah, I already told or talked about the cases when that we are talking about. There might be node failures, there might be cluster patches.
I'm fine. I am on Java conference. Yeah.
Just have some.
No, I put on hold my conference session.
Yes, Wimmers, just. Can you mute? Okay, thanks, great. Then I already talked about the cases in which these issues might arise, so cluster patches, node failures. And the point what to do about this is to configure so-called topology spread constraints. Hard word. So what does this actually tell us, this configuration? It tells that pods with specific labels, in this case, my app, have to be distributed among different workers with different labels. So, for example, based on a label zone, there might, or you have to, Kubernetes must only deploy the pods in a way that there is a maximum difference between different zones of one. So, for example, with our 4 pods, we can't have 4 pods when we have 2 different zones. Then we can, then 3 and 1 is allowed because the max difference, the max skew is 1. But 4.0 is not allowed because then 3.1, okay, no, 3.1 isn't allowed. 3.1 is a skew of 2. I can't count at the moment. So 2.2 is an allowed scenario. 3.1 is uncool because max skew 1, the difference is 2, so it isn't allowed, and obvious 4 and 0 isn't allowed too. So this is a great way to actually dispatch the nodes or the different pods, the different containers of an application on different nodes, and to also have them in different availability zones, for example. And the next thing to be aware of is that Kubernetes actually handles or treats updates or deployments differently than when nodes are taken down. So when you configure a rolling update, it's great when you actually deploy a new version. But it's bad, or it has no effect when a node is scaled down because the workload isn't needed anymore, or because it has to get patched. What you have to configure that you don't have, or that you don't have a problem with the availability of your application, is the so-called pod disruption budget. That's the property, or that's the thing that actually tells Kubernetes in this example that pods with a specific mesh label of app and the value my app, that you only allow 1 unavailable pod at any given time. So when nodes are being shut down for maintenance, or when nodes are failing and other nodes are shut down for maintenance, when your max tolerated unavailability is greater than 1, Kubernetes waits until more pods of your application are running. So that's the hint back to having configured startup probes, readiness probes, that Kubernetes can actually tell when nodes are available. So, and now we talked about technical mitigations to potential unavailabilities. But of course, you could, for example, choose complete different architectural approach like serverless. I mean, there's always a new instance created for each and every request. You can, we could talk about things like failovers in our code, retries. We could cache requests to other services, or our front end could cache, or we deploy special caches. We increase the loose coupling of our services. There's lots of things we can do to actually make things easier, but they all come with different challenges. So there are three really important components for zero downtime. The first thing is awareness. Just because we're in the cloud doesn't mean that everything is always there, is always available. Our applications have to be able to handle this. Our deployment configurations have to be, or have to take care of server failures, of patches of our platform. And of course, our applications have to be able to handle lots of shutdowns, lots of restarts without affecting the user. The second thing is, when something goes wrong, something goes wrong. No one's perfect. So we need an error culture. We just cannot, or we have to talk about the failures that happened. Because first of all, other teams can learn from them. And second, we also have to fix those things. We need time for that. That's time that's missing for delivering new features. But still, the availability of our services is important. So we need a culture where you can talk about errors and where you get time to actually address your problems. And of course, when we have all those things that are really on a soft skill, issues, then of course we can talk about technical mitigations. And with all this in mind, we won't get real zero downtime, but we can get close to it. And that's it for what we wanted to show you, or what I showed you today. There are some tweaks, hopefully in Kubernetes, that you are aware of now. There are things you are aware of now. And I thank you all for joining my talk today, and have a great day.